Hey everyone, I'm Sathya and this is Jakob. We work on V8, which is the JavaScript engine in Chrome. Today we'll be giving a high-level overview of the execution pipeline in V8.
So buckle up, you're in for a ride. We're going to start with some terminology and then take a look at the various stages of the execution pipeline, from the parser to the interpreter to the object model to inline caches and finally optimization. Then we'll talk a bit about memory management, the dev tools, profiling of websites, and ongoing work in our team. So V8 is Chromium's ECMAScript implementation, better known on the internet as JavaScript. It includes support for ECMA 402, that's the internationalization API, and these days also WebAssembly. In addition to Chrome, V8 is used by Node.js and a bunch of other embedders, for example, Steam or Visual Studio Code, anything using the Atom or Electron editor frameworks. In Chrome, we use a convenience library for interacting with V8, which is called Gin, rather than the V8 API itself. Gin, in addition to the renderer, is also used by Chrome extensions, PDFium, and the proxy auto configuration in the network stack. Blink layers yet another library on top of Gin, which are the Blink bindings. They are mostly a bunch of auto-generated glue code bridging the worlds of all the DOM objects that Blink is responsible for with JavaScript running inside V8. An instance of V8 is called an isolate, and there can, in theory, be many per process. That's why we have them, but Chrome mostly uses only one, except when you have a web worker that gets its own isolate. Within isolates, there are contexts. Every object is part of a context. There's one context per iframe. In particular, that means there can be many objects per isolate. Specifically, if you run extensions that inject content scripts and you have several iframes, then every extension for every iframe gets their own context. So you can easily have 100 contexts per website. Within the Blink bindings, working with all of that is simplified by encapsulating it all in a script state.
So the first step of the execution pipeline is to get the script text. The embedder provides a script text. V8 doesn't know how to download the script. So the embedder, which is Blink, provides a script from either the network, cache, or the service worker. V8 can sometimes also cache the bytecode. So for warm loads, we can bypass the parsing and just load the bytecode. And V8 also has a streaming parser. So we can parse the script as it's being downloaded. So we hide the parsing cost in the network layer. So once we have the script text, the next part of the pipeline is the parsing. So we parse the script text to output an abstract syntax tree. So V8 scanner decodes source text in UTF-16 format. The scanner tokenizes the input and produces a stream of tokens that's fed into the parser. So the parser itself is a recursive descent handwritten parser. The parser produces the abstract syntax tree. V8 has two different parsers, a full parser and a pre-parser. The pre-parser does a syntax parse, some early error checking, and partial scope analysis, but it doesn't create the AST nodes. So this lets us defer the cost of fully parsing a function to improve startup time. So let's look at an example of what the parser does with source text. So in this function, we have a variable declaration, assignment, and a return statement. And this is the abstract syntax tree. That's the output. So first, we have a function literal AST node for the function itself. And then we have a block for the function body. And then we have a variable declaration AST node to denote that we're declaring a variable B. And then an assignment AST node to denote that we're assigning the literal value 1 to the variable B. And finally, we have a return statement. Variable proxies are references to variables. At this point in parsing, all these variable proxies are unresolved. So we don't know that they're actually pointing to the same variable. So in addition to the AST, the parser also collects scopes. The scopes contain a list of declared variables. So for the global scope, it contains the function foo, and the function scope itself contains the variable b. And each scope also has a list of unresolved variable references. So once parsing is completed, we run scope analysis, which connects the unresolved variables to the variable declarations. So at this point, we'll figure out that actually all the variable proxies point to the same variable B. The next part of the pipeline is the interpreter. So as we previously saw, the output of the parser is the abstract syntax tree, which is fed as input to the bytecode generator. The bytecode generator, as you can imagine, generates a stream of bytecodes. And the interpreter executes one bytecode at a time. So there are several ways to build an interpreter. So for example, we could have a simple interpreter which has a huge switch statement, and each which specifies what to do for each bytecode. V8 has an indirect threaded interpreter. The interpreter has a table of handlers keyed by the bytecode. So the interpreter looks up the handler for a particular bytecode, jumps to it, and then starts executing code. The bytecode is the source of truth for the interpreter, optimizing compiler, and the DevTools. So we record several kinds of metadata in the bytecode itself, like source position and the handler table. So once we have the bytecode, we can throw away the AST that we generated, saving memory. The bytecodes have been carefully selected to represent JavaScript efficiently and compactly, because memory saving was one of the big goals of our interpreter. It has a single accumulator register that most operations reference. So in this example, we have a text equals strict bytecode that uses the accumulator as an implicit argument, and its second argument is the variable a that's passed to the function foo. There's also a stack pointer updated once per call frame, which provides a base for a number of stack-based registers. These aren't machine registers. These are often the local variables of the function. JavaScript objects, which are allocated on the JavaScript heap, can't be directly embedded in this bytecode. So we have a fixed array called the constant pool, and then we embed the index in this constant pool in the bytecode. The optimizing compiler in V8 ships with a code generator, which uses a custom machine-independent portable assembler. So the interpreter uses this assembler to generate code for each bytecode. So we get portability and interop with the optimizing compiler. And this also fits into the lowest tier of our optimizing compiler, so we get some optimizations for free. And this is an example of how a handler for a bytecode is generated. So in this example, first we get the register index by looking up the next byte of the bytecode, then load the register and the accumulator, and then call the add stub, which generates code for the JavaScript add operation, as specified by ECMAScript. And finally, we store the result in the accumulator and then dispatch to the next bytecode.
Once we have bytecode, we can execute it, and at the same time collect type feedback about it, and I'll explain you how that works. JavaScript is a dynamic language. That means pretty much anything can change all the time, object shapes and property chains and whatnot. And also, even seemingly simple operations like property loads have quite complex semantics. For an object.foo load, like here on the first line, it could mean just loading a simple property from the object. It could mean calling a getter. It could mean walking up the prototype chain. There could be proxies involved or whatnot. Figuring out what to do dynamically is relatively slow. And so the way to speed that up is to cache it and hope that the same code will always do the same thing. In order to achieve that, what the bytecode does is it calls a getProperty stub, which is given the object, the name of the property, and 2 slots in the feedback cache. If the feedback is not there or doesn't match the current object, then it has to perform the dynamic lookup, and it can update the cache for the next time. If the feedback does match the current object, then the second slot in there will contain a bit field that encodes exactly what to do, no dynamic lookups required. Let's look at an example. For this function here, for the one property load that it has in there, we reserve 2 slots in the feedback vector, which are associated with this one load. If there were several loads, then each load would get its own 2 slots. At first, these slots are uninitialized. When we call the function with an object, then the shape of this object is cached in the first slot, and the bit field containing what to do, where to find the property and how to load it, is put into the second slot. When we call the function with another object, it would be invalid to just do the same thing. This object is different. It doesn't even have a foo property. We have to return undefined. The way this is handled feedback-wise is that we put a polymorphic sentinel into the first slot, and the second slot becomes a pointer to an array that contains several pairs of object shapes and bit fields telling us how to handle them. So all of this requires being able to detect and track object shapes. So let's take a quick look at how that works. When you create an object in a JavaScript using a constructor function like this one, we at first create an empty map for it. Map is our internal name. Object shape is kind of the most descriptive term. In previous external documentation, we've called it hidden classes, which reflects the fact that it's kind of similar to classes that you have in other languages. These days, there are also classes in JavaScript, so that term becomes a bit overloaded and possibly confusing. So now we prefer to call them shapes. At first, the map is empty because there are no properties. When the constructor adds the first property to this object, we create a new map that contains information about this newly added property, where in the object to find it, its name, and any attributes like whether it's read-only. We also create a transition from the previous map, which was empty, to the new one that knows about this property. Because the whole point of this is that all objects coming out of this constructor function will have the same shape. So they have to be able to reuse the maps that we created for the first object. So we add these transitions to make that possible. Same thing then happens for the second property. New map is created, new transitions inserted. The object is migrated to point to that new map, and we're done with this. The beauty of the system is that not only does the caching in inline caches make execution of bytecode faster, we can also use it as input for the optimizing compiler, which is called turbofan, to generate optimized code based on the type feedback we've seen so far. Turbofan is a sea of nodes, graph-based compiler. That's the very latest in optimizing compiler technology. Sea of nodes means that all data dependencies, control flow dependencies, and side effect dependencies are expressed as nodes being input to each other. So the nodes representing high-level or low-level instructions at first don't have a fixed schedule. They're scheduled relatively late. All we know at first is which node depends on which other node, and that gives us maximum flexibility for applying optimizations. In V8, we compile functions individually, so we don't compile the entire program at once. Instead, we wait until any given function has spent enough time in the interpreted code that we think that optimizing it is probably worth the time spent on it. And as Sathya already mentioned, the nodes graph is generated from the bytecode, so we don't have to build the AST again. Turbofan works in several stages where it lowers the nodes graph from the initial high-level representation to optimized machine code as the end result. In the JavaScript level of nodes, the abstraction level represents roughly JavaScript operations. For example, load this value from this array. That's then lowered to a simplified intermediate state where, for example, the array load might be split into a bounce check and then the actual load, assuming that the bounce check was successful. That's then further lowered to a machine level graph, which contains nodes roughly on the abstraction level of individual assembly instructions. And that is then compiled to machine-specific actual assembly. So only the last bit is different on different architectures, and all the earlier stages are shared. These are some examples for the optimizations that we can do in Turbofan. For example, we can fold constants, replacing 3 nodes with 1. We can do strength reduction of operations to make them faster. We can use global value numbering to eliminate duplicate computations. And we can even do algebraic reassociation and other reorderings of operations if that leads to more efficient overall code. That is supposed to be a plus sign hidden behind their black box there. There is one crucial bit missing in the execution pipeline as described so far, and that is de-optimizations. By its very nature, optimized code contains lots and lots of assumptions based on type feedback that has previously been collected. For example, if we have seen an addition that can do many different things in JavaScript, to always have added integers, then we will emit optimized code that always assumes that it's an integer addition. If such an assumption does not hold, and optimized code contains a bunch of type checks to guard this, we require a fallback. For example, if code suddenly passes in a string and we have to add a string and an int, that obviously requires very different code from a plain integer addition. The way to handle that, or the way we handle it, is to de-optimize. That means throw away the optimized code because it doesn't know what to do, go back to interpreted code, and resume execution there, updating type feedback for an eventual possible later round of optimization. For this purpose, we need to associate a bunch of metadata with every point in optimized code that can cause a de-opt so that we know which state interpreted code would expect if we had to resume from there. All right. Another very important area of V8's responsibilities is memory management, keeping track of all the objects in the heap and cleaning them up when no longer needed. So let's talk a bit about that. V8's heap uses a generational layout. That means it has a new space for freshly allocated objects. This is up to 32 megabytes on desktop platforms, the assumption being that most objects die young. There's also an old space for longer-lived objects. That's up to 2 gigabytes currently on desktop platforms. And separate from that, there's code space, which is special in that it's executable. The rest of the heap is not executable for security reasons, but when we want to generate code, we have to have some executable area. V8 uses a tracing garbage collector as opposed to reference counting. That means a GC cycle follows all pointers to find all reachable objects, and any objects that have not been reached by following all pointers are considered dead, and the respective areas can just be marked as free. We're aiming for both low latency and high throughput, which are often conflicting goals. In order to achieve that, the garbage collector does as much work as possible incrementally, in parallel, that means several threads at once, and concurrently, that means in the background. And the team is constantly working on moving more and more in that direction. V8's GC is also tightly integrated with Blink's OilPan GC. It turns out that it's fairly difficult to have two independent GCs in the same system, because it's easy for them to just assume that any object required by the other side of the fence is still alive, but that can lead to cycles that can then not be collected. And so we need pretty tight integration to make it possible to detect such cycles and be able to clean them up when they're not otherwise needed. In NewSpace, we run so-called minor GC cycles. NewSpace is organized into two halves, and a minor GC moves all the live objects from one half into the other half. Any object that has been moved before is instead promoted to old space. The typical pause time of that is less than 1 millisecond. If we need to clean up old space, then we run a major GC cycle across all spaces. It first has a marking phase where it finds all the live objects. This is done incrementally in many small steps, easily up to 100 or more. Then it has a sweeping phase where, when marking is completed, all the objects that have not been marked can be added to the free list. This happens both in the background and with several threads at once. It sometimes does compaction. That means on an almost empty page, all the remaining objects are evacuated onto some other page, and the page is given back to the operating system. We try to avoid that because it tends to be slow. The GC also needs to update references. Anytime an object moves around, any pointers referring to that object need to be updated to refer to the new location. And this leads to a maximum pause time of that last atomic pause of about 8 milliseconds or less.
So as Jakob mentioned earlier, V8 also provides an implementation of WebAssembly. WebAssembly is a low-level execution format that is designed to be used as a compilation target. So currently, memory-managed languages like Rust, C++, and C can be compiled to WebAssembly. WebAssembly is both a text and a binary encoding. The text encoding, there's a 1:1 mapping between the text and the binary encoding, and the text encoding is mostly for debugging, whereas the binary format is fed into the engines as input. This example is similar to a JavaScript function that takes an argument, multiplies it by 2, and returns the result. But this is already specified or specialized to work with 32-bit integers. The WASM implementation V8 has 2 tiers for compiling and executing WASM. The first baseline tier is called liftoff, which compiles code very, very quickly, which helps with startup performance. The second tier is turbofan, which is incidentally the same backend that we use for optimizing JavaScript. The code generated by turbofan is twice as fast as the code generated by liftoff. WASM provides a validation step that provides guarantees that there's no de-optimization required, which is different from JavaScript. V8 also provides the backend of the Chrome DevTools. So apart from basic debugging functionality like breakpoints, single stepping, it also supports live edits, so you can edit the code and change the code on a running page without having to reload it. It also includes other powerful like tools such as a sampling profiler for looking at performance profiles, and heap snapshot and allocation profiles for understanding memory usage. So we've seen all the various parts of V8, but where does V8 itself spend its time during execution? Traditional benchmarks spend a lot of time executing JavaScript in tight loops, leading to a profile like this, where we spend most of the time executing optimized code. So there's a lot less time spent in the runtime, which is the V8 C++ chunk, or parsing. But looking at the loading profiles of real-world websites, we see that the profile is very different. For example, we spend much less time in optimized code and much more time in parsing and the runtime compared to the previous Octane benchmark. So we pick areas to like focus on and optimize based on these observations. So we saw where V8 spends its time, but where do the V8 developers spend their time? So we're always implementing new language features as they're being standardized in TC39. There's also a lot of work being done on improving the latest features that were implemented, like async await. Another increasing important priority is reducing the memory footprint of V8, which helps mobile devices. So, and for WebAssembly, on the toolchain front, we're helping integrate WASM into LLVM. And on the standards front, we're helping develop threads and SIMD. So this was a very high-level overview of V8. Please come talk to us, or like if you have any other questions, or if you want to learn more. Thanks. So for TypeScript, the type system in TypeScript is not sound, which means we can't use the guarantees of the type system to generate code, which means it doesn't really help a lot with performance.
Yeah, in general, the type of types that you have in TypeScript are designed for developer productivity, and there are different requirements from the kind of types that a JavaScript engine needs to apply optimizations. We actually had someone work on a prototype for, I think, almost half a year to see what we would gain by consuming TypeScript directly, and we put the project on ice because it doesn't lead anywhere. How do we decide when to tire up the turbofan? We essentially count bytecodes executed. I don't think I think it's pretty precise. At backwards jumps and at function exit, we know how many bytecodes we've executed, and so it's based on the assumption that every bytecode takes approximately the same time, which is not quite accurate, but accurate enough. And it boils down to something less than a millisecond per function, but I don't know the exact number. Any other questions?
So you optimize the functions in the background with Java. So like JavaScript is running, and then you decide, oh, this function is hot, let's optimize it. It does the optimization, then you just switch in the bytecode?
Essentially. So we need to start the optimization process on the main thread when we build the graph that requires heap access. We're working on putting it in the background, but it's difficult. The main optimization then happens in the background, so we keep executing bytecode while optimization runs. When optimization is finished, what we prefer to do is next time the function is called, switch over to optimized code. If it's a long-running function with a long-running loop and we want to replace it as it runs, then we do have a technique called on-stack replacement, OSR. But we need to specifically compile for that so that there is an entry point into the middle of the loop. So that's separate.
I can take this. So in this case, the parser, so the way we implement this in V8 is the parser desugars this into property access. So we create a temporary variable that stores the argument and then does like temp.opt1 equal to, opt1 equal to temp.opt1. So all of the property access optimizations just follow through with this. This is one of the advantages with doing parser desugaring. So we don't have to do specific optimizations for these.
Yes, sir.
Are there any opportunities for using machine learning, like for the optimizers?
That's a good question. It is essentially a classification problem or decision-making problem. Do we optimize, yes or no? I suppose you could, but it would be difficult to come up with a decent training set. And the internet is very big, obviously. There are many different websites with many different JavaScript programs running on them. It might be a worthwhile experiment to see if with a machine learned system you can get better results than with the hand-coded heuristics that we currently have. It probably doesn't make all that much of a difference. One key insight there is that optimization decisions, they do matter, but they're by far not the only thing that matters. And so even if you turned off the optimizing compiler, the average loading performance of a website might be anywhere from constant to maybe 2x slowdown or so. We see, so for hot code, tight loops, maybe online games or whatnot, the difference between bytecode and optimized code is 10x, 20x or something like that. But for average browsing around, it almost doesn't matter.
You talked when you were specifying like shapes and so on, and you're tracking a cache. You said something like a cache vector that you allocate two parts of. So what's that cache vector? Is that like for the entirety of V8 contexts? Or?
Every function essentially gets an array for the type feedback, and we call that the type feedback vector.
I see. And is each entry for a function parameter or the argument that's actually passed? Like, what are you storing the type shape for? Like, so function.
We track the shape of objects. And in this type feedback vector, every operation that depends on a type feedback gets a few slots. It's typically 2 or 3 slots per operation. So for example, when you have an addition in your code, that addition operation gets 1 slot, 2 slots, I'm not sure. So that it can, for example, keep track of, has it seen integers, has it seen strings, has it seen objects, has it seen doubles. Every property load gets 2 slots. That's the example I showed. In the first slot, it stores the map of the object that it has seen. Yes?
So you mentioned you have your lowest tier interpreter and your high tier optimizer. Is there anything in between the two, or is it just?
V8 only has 2 tiers. That's not the same across all JavaScript engines. I believe Firefox has 3 and Safari has 4.
Yeah.
It's a trade-off, mostly implementation complexity versus how many degrees of freedom you have. Our experience is that we do not want to have more than 2 compilers because it's too much effort to maintain them, and it doesn't give you all that much benefit.
Looks like we're out of time. Thank you.